Hello, welcome to Electronics Education. This is Vincent Chang. In this lecture, I'm going to teach you how to solve a feedback amplifier. The key concept explained. This is part one. How to solve a practical feedback amplifier. Let's still start with the ideal series-shunt feedback. For example, for the ideal series-shunt feedback, Vs minus Vf equals Vi. Look at the circuit diagram. And then times AV, which is the gain of the voltage amplifier, goes to the output voltage. And then there's a sampling network, shunt sampling, take the output voltage and send it back through the feedback network times the beta, and it goes to generate a feedback output, the feedback signal, the voltage feedback, Vf, and go into the mixer and form a closed loop configuration. And then we can consolidate, reduce the complete, sort of a little bit complicated on the left-hand side, into a more simplified version of the ideal series-shunt feedback. And then here's the outcome. The outcome about RF, the closed loop voltage gain, and RF. You should be very familiar with this. But the key point is the ideal. What is the meaning behind the word ideal? What's the meaning behind that? So ideal structure, there are two fundamental assumptions. Two fundamental assumptions. Number one, remember the two fundamental assumptions. Number one, the open loop gain A is independent of what? Independent of signal source, an external load, and also the feedback network. The open loop gain A is independent of signal source, external load. In other words, when you change the source, when you change the load, when you tune the feedback network, the A won't be changed, won't be affected. And another one is A is only responsible for, it's the unilateral, it's the unidirectional transmission for A, and unidirectional transmission for beta. But in reality, let's consider a practical, it's not ideal. It's the practical series-shunt feedback. Let's say we have the basic amplifier, the BA, the basic amplifier. Here's the equivalent circuit. To help you not get confused or mix up with, so I do this on purpose. Okay, I use the lowercase r represent the input resistance of the basic amplifier, and the lowercase r, RO, to represent the output resistance of the basic amplifier. And also the GV means the voltage gain for the basic amplifier. You will see why I do this in the coming slide. Okay, and now let's include the signal internal resistance of the external signal. There's the source resistance. Also, let's include the load, external load. And also the beta is no longer ideal voltage control voltage source. So how to model a real feedback network? Let's adopt. Let's take the so-called H parameter model. H parameter model. H parameter model for the independent variable is the input current and the output voltage. And the dependent variable is the input voltage and the output current. I1, V2 is independent. And the V1, I2 is the dependent. So there's a matrix. H11, H12. H21 and H22. What's the meaning of these two H parameters? For the H11, it's the input resistance. For the H12, it's the reverse voltage gain. For H21, It represents the forward current gain. H22 is the output conductance. Again, it's the input resistance, reverse voltage gain, and forward current gain, and the output conductance. If I'm going too fast, if you want to pause, just take a note. All right, and think about, okay, H11, V1 divided by I1, V1 input voltage divided by I1. Oh, okay, Vincent is right. It's the input resistance, right? Okay, so now, here's the problem. So how are we going to solve this? That's the problem, right? Because it's got complicated. So how are we going to solve this? Because we are far from the ideal. The lesson we learned from the past only teach us how to tackle the ideal structure. But in reality, it's not ideal. Then the goal is to simplify. Is to reduce the complication to a more simple version. All right, that's the goal. So we are on the path of simplification. All right, we are going on the journey of simplification. Okay, so how to simplify this? The first one, let's neglect this. Because for what was this? I said, what's the meaning of this the third H parameter? It's the forward current gain. It's the forward current gain. So for the feedback network, it's major. The primary responsibility for the feedback network is to go doing the reverse transmission. So usually for general purpose, the resistive type of feedback network, the forward transmission is negligible. We can neglect that. We can neglect the forward transmission of the feedback network. So let's assume the H21 is 0. So it's an assumption, all right? It's an assumption. It's an approximation. It's an approximation. But it's acceptable for most of the cases. And now, we're still a little bit complicated, right? How are we going to deal with this? Because we neglect this, then we can take out the H21. We can open the current source. And now, the next step, what do you see? What did you see? Let me go back. Okay, do you see something is changing? Okay, can I move one step backward? Can I do this? Can I? Of course I can, right? Because they are equivalent to each other, right? It doesn't matter. And then what? Then what about this? It doesn't matter, right? They are equivalent. They are equivalent, right? I didn't change anything. I just place, just come closer, okay? Let's come closer. Equivalent, okay? I'll now focus on the RL. Can I do this? Can I? Of course I can, right? What about this? Of course, they are equivalent. I didn't change anything. They are, of course, in the geography, that's not, they are equivalent. But electrically, they are equivalent. Electrically equivalent. Electrically equivalent. Okay? Let's focus on the third one, the H11. H11, can I, the most, let me tell you this. Let me encourage you a little bit. Okay. Again, when I was a college student, I didn't really know. Maybe I can solve a feedback amplifier feedback circuit, but I don't know why. I really don't know why. Because no one told me this. I really don't understand why. Now I'm teaching you why. Why? Before you harness the skill to solve a feedback circuit, you got to know why. I'm teaching you why. All right, so the H11, now let's focus on the H11. Can I do this? Yes. Electrically equivalent. Can I do this? Yes. Vincent, you can. What about H22? Can I do this? Too quick? Can I do this? Can I do this? Electrically equivalent. You can say it doesn't matter, right? Because they are electrically equivalent, but it matters when it comes to solve this. It matters. So now, here comes the most beautiful part, okay? Let's now do this. Let's redefine the A, the open loop gain A. Let's redefine the A. Because if you just looking down, if you sit in the basic amplifier and looking down, what do you see? What do you see? You see a voltage control voltage source, right? Oh, aha moment. So beta now is defined by a parameter called H12. Get it? Get it? You get it? This is very important. The beta, the voltage control in ideal case, you still think about the ideal case. Our job right now is to on the path of simplification. Try to reduce the complication to a more simple one. And what's the simplest one? Ideal case. So now it's the voltage control voltage source. And also we rename the, because there are different topology. So we want to have a unify the input resistance. The symbol for unify, because for Series-Shunt, here's the truth. For Series-Shunt, you're going to use the H parameter. For shunt-shunt, you're going to use the Y parameter, Z parameter, so different parameter. So it's too complicated. Let's just, for the input resistance, let's use the RA. For the output resistance, let's just change the symbol, use the RB. And then you see the orange part, series mixing. For the green part, shunt sampling. So here's the most important part. I said, let's redefine the A. This is the A. Let's redefine the A circuit. Redefine the A. Redefine the open loop gain. So what is A right now? What is A right now? So if you just treat the A as a black box, if you treat the A as a black box, okay, so don't worry about the complication of the inside, something inside with the, it's a little bit messy within the black box. But looking outside, looking outward, what do you see? You see series mixing, ideal case. Shunt sampling, ideal case. And looking down, voltage control, voltage source. So it's the path of reduction. It's the path of reduction. So now let's try to clean up the black box. Okay? So we can just combine the three resistance on the right into the one, the capital R, I. And also the three resistance on the right on the output of the right hand side. The previous one is on the input. Let me go back. I said, let's focus on the input side of the right hand side. There are three resistance, right? So we can combine into one single one, capital I. And also there, in the output side of the right hand side, there are three also resistance, RB, L, and lowercase RO. Let's use the one capital RO to represent the 3, and redefine the AV, the voltage gain. It's a successful reduction. And the relationship, the 3 series combination of the 3, capital I. Also the parallel combination. Now, let's pause a little bit. Give you some time to digest. Let's pause. I think 2 minutes is good enough for you. Figure out what is capital R here in terms of the original parameter on the practical series feedback amplifier on the right. So how to represent the AV on the left in terms of the parameter on the right. So, 2 questions, all right? 2 questions. Try to find out the capital Ri, the input resistance, and the closed loop voltage gain. Let's pause. All right, I'm back. For the Ri, there's no problem. Based on the Thévenin Theorem, you can simply solve this. The parallel combination of the 3, BL and the lowercase RO equals the capital RO. And here's the relationship between AV and the GV based on the Thévenin theorem. But you have to find the relationship between VI and the VB. Find the relationship between VI and the VB is the divider. The VI and the VB is the relationship of the divider. Okay? The I divided by SA and the lowercase I. So, because we have successfully reduced the complication, the practical case, into ideal one. On the left-hand side is the ideal case. So you can just courageously, boldly apply the simple result from the ideal case because you have done a successful reduction. You can just time the 1 plus A beta for closed loop input resistance and divide by 1 plus A beta for the closed loop output resistance. Same thing with the gain relationship. So here's the takeaway. For practical feedback amplifier, our job is to understand. So the keyword here, there's only one keyword, reduction. So reduce a complication into an ideal one. So this is the ideal case. So takeaway number 2, because if we treat the blue one as a black box, then it becomes the ideal. So our job here is to find out the relationship between left-hand side, the simple the network, and the right-hand side. We have done this. Here's the result, the final outcome. I know this lecture is, as if you feel kind of uncomfortable, kind of challenging, intimidating for the first time, I think it's not rare. It's not unusual. All right, many students suffer this for the first time. But if you listen, I encourage you maybe just watch the lecture video again and try to digest the key concept. What's the meaning of the simplification, and reduction? So we try to use what we learn, move on to the next lecture and solve. Try to cultivate the skill to solve a practical feedback amplifier. I hope you really learned something from this lecture. Thanks for watching.